Hello, my name is Martin Škokainis, and in this video I will talk about our recent result concerning quantum walk-based quadratic speedup for the search problem in graphs. And this is our joint work with Andrew Sambains, Andrus Gillian, and Stacy Jeffery. Usually hearing words quantum search and quadratic speedup, Grover's algorithm first comes to mind. And Grover's algorithm is applicable when we wish to perform exhaustive search in an unsorted database. Suppose we have a finite search space, say of elements, and some of these elements are interesting to us, and we wish to find any of them. For simplicity, we'll call these elements marked. So we have an unsorted database, and we need to find a marked element. And at any moment, we can access and check any of the elements in the database for being marked or not. In a classical computer, we will need to check essentially every element in the database before finding a marked one. However, on a quantum computer, Grover's algorithm allows to find a marked element essentially quadratically faster than classically. However, this algorithm does require that we are able at any moment to query any element in the database and check if it's marked or not. That might not always be the case. It may be possible that after checking some vertex, we are able to check some neighboring vertex, but not an arbitrary one. Such setting is not uncommon when it is easy to update the current position to a neighboring one, but it is difficult or expensive to check an arbitrary vertex as required by Grover's algorithm. And in cases like that, the best way forward could be simply randomly wandering around the graph. And for instance, suppose you are lost in a city and you wish to find your way back to your hotel. With no map and no mobile internet, and even being too shy to ask anybody for directions, what you might just do is explore your surroundings by wandering around the city. And let's make matters even worse for you. Suppose you have terrible memory, and at every new location, you quickly forget where you were before. And that's why at every intersection, you just choose a random direction. This algorithm of wandering around by choosing a random direction at every new location is well known among classical algorithms. The highly technical term for this process is drunkard's walk, sometimes also called random walk. And at any instant, the random walker has only local information about their immediate surroundings. When the walker reaches a new location, a new intersection, then they possess only local information about that intersection. But they don't remember where they were before and what places they have visited before. And this memorylessness is exactly the thing that characterizes the random walk. If you wander around long enough, at some point you will reach your hotel, you will solve the search problem using random walk. Obviously, this is probably not the most efficient way of finding something, but sometimes it is the only way we know how. And in cases like that, I might naturally wonder just how long this process will take, how many steps of random walking before we find anything. And generally speaking, the answer depends on the graph, on the location of the marked vertices, and this expected number of random walking steps is called the hitting time. And many actual such problems are such that they use random walking as a subroutine. And in problems like that, analyzing the hitting time can give us an upper bound on the complexity of the algorithm. And as was remarkably shown by Zegedi, roughly 15 years ago, any algorithm that can be modeled as random walk on some graph, there's a quantum counterpart termed quantum walk, which detects the presence of marked elements quadratically faster than the classical random walker. Now, this correspondence between classical random walk and quantum walk requires that the classical random walk is time reversible. That is, it satisfies the tailed balance equation, meaning that when at the stationary distribution, then the probability of moving from one vertex to another is the same as moving in the opposite direction. And how long do we run this random walk? We do that for a time which is constant multiple of the fitting time. And the fitting time is formally defined as the expected number of steps to get to a marked vertex, starting from a vertex which is chosen at random according to the stationary distribution. And for many quantum algorithms, quantum walks is an important subroutine of them. And among the first applications was the solution to the element distinctness problem. In element distinctness, we are given a list of numbers, and we are asked if there are any two equal numbers. Classically, we will need to take a linear number of steps to find the answer. And quantumly, applying a quantum walk on Johnson graph allows to find the answer more quickly. And so in element distinctness, this quantum walk-based algorithm is actually optimal. Number of queries made, and quantum walks have proven to be a useful tool also for many other quantum algorithms. Well, that usually happens when the problem at hand can be modeled as searching some locality constraints. And here are a few examples of algorithms which have successfully used quantum walk on some graph. But let's return to the general case of some general graph and the corresponding random and quantum walks. So the result by Segdi states that for any random walk, the corresponding quantum walk detects the presence of marked elements quadratically faster than possible for the classical random walker. There's an important caveat. The quantum walk does not actually find any marked vertex. It just detects that there is any, there is not. And classically, it is probably difficult to even imagine how could we detect the presence of marked element without ever finding any. And that's because in the classical setting, both detection and finding problems are solved the same way. We just wander around the graph until we literally step on a marked vertex. But actually, there's a simple explanation why quantum walks can detect the presence of marked elements, but not necessarily find any. And the quantum walk starts in a certain state, and if there are no marked vertices, the quantum walk will the state intact throughout all the quantum walk. However, if there are marked elements, with each step, the starting state gets rotated, ever so slightly. And that's not unlike Grover's algorithm, for instance. However, when we have made enough steps, nearly square root of t steps, then the state has been rotated enough. It has been rotated to a state which is nearly orthogonal to the starting one. And that means that we can distinguish the state from the original one by measuring it. And the measurement answers us if the state coincides with the starting one, meaning there were no marked elements, or we have a different state, which means that there were marked elements. And that solves the detection problem. But why we do not find any of the marked elements? A tempting idea would be to measure the state in vertex basis and hope that the measurement would yield a marked vertex. But this intuition is false, because it is very well possible that this final state has a very tiny overlap with the marked states. And measuring it and doesn't reveal anything about the marked vertices. So quantum walk can detect the presence of marked elements, but not necessarily find any of them. And that's unfortunate because usually we are more concerned with finding desirable things, not just detecting there exist any. So how do we solve the detection problem? How do we find a marked vertex in time square root of the classical heating time? If there's only a single marked vertex, that case was subsequently solved, first in 2008 by Magnus, Nayak, Richter, and Santa for state transitive graphs. In that setting, if there's only a unique marked vertex, that can be found relatively faster than classically. And later Crowley, Magnus, was also Roland, saw this case of a single marked element for any graph. And they did it by inventing a new novel technique called interpolated walk. So when there's only a single marked element, you can always find that quadratically faster than classically. But what happens when there are multiple of them? Then we're not guaranteed to find any of them quadratically faster than classically. Here it should be mentioned that the algorithm by Crowley, Magnus, Oswald, and Roland actually does find a marked vertex, even when there are several of them on any graph, but the algorithm works in time which is square root of a quantity called extended heating time. And this extended heating time might coincide with the classical heating time from random walks, but it might be also something different, namely larger. In fact, it is possible even that the extended heating time, the square root of the extended heating time, is much larger than the classical heating time. And that means that the quantum algorithm even takes longer than the classical random walk. And there's no quantum advantage at all, let alone quadratic. So the case of multiple marked vertices, this case remained open prior to this work, where we finally prove that indeed, for any graph and any configuration of marked vertices, quantum walk can always find one of the marked elements in time which is essentially square root of the classical heating time, up to logarithmic factors. And how do we do that? Here are the basic ideas. First, we modify the original random walk to behave it differently at marked elements. Here's an example of a random walk on a graph with 6 vertices. One of them is marked, and we need to model the requirements that the classical random walker at the marked state, when it reaches the marked state, it doesn't leave it. And this is usually done by ending a self-loop at the marked element, so that when the random walker reaches the marked state, it stays there with probability 1. This random walk is called absorbing walk, and it is the actual random walk that is applied by the classical search algorithm. But the quantum algorithm actually uses a fusion of these two walks. It uses so-called interpolated walk. The interpolated walk was invented by Crowley, Magnus, Oswald, and Roland in their attempt to solve this problem. And when we apply the interpolated walk, then we stay at the marked element with a large probability, but with some probability we move to a neighboring vertex and we perform these steps then according to the original walk. So the interpolated walk is essentially a convex combination of the absorbing walk and the original walk. Now the other tool we apply is a recent algorithm by Simon Ebers and Alan Serlet called quantum fast forwarding. The quantum fast forwarding algorithm allows to apply t steps of a classical Markov chain quantumly in order square root of t steps in a certain sense. And the certain sense is that you generate a state that would be obtained by applying t times the discriminant matrix of the reversible Markov chain to the starting state. Now the discriminant matrix is symmetric, similar to the transition matrix, and its elements are defined as a square root of the respective transition probabilities. And a further caveat is that this target state might be obtained only with a tiny probability. And that's because the discriminant matrix is not unitary, so the algorithm actually generates a normalized version of the target vector, but it does so with probability, which is the squared norm of the target vector. And if this norm is small, then so is success probability, and it may be the case that we obtain the desired vector only with some small probability. First, and how do we apply these two things? For the sake of this presentation, I will assume that the transition matrix for our random walk is symmetric, which means that the discriminant matrix coincides with the transition matrix and the stationary distribution is uniform. And then we generate the state superposition of the unmarked vertices, and we intend to apply these steps of the random walk to this state and project it onto the marked states. And our claim is that for a suitable choice of an interpolation parameter, the resulting vector has large norm. And not only the norm of this vector is large, but it also has large overlap with the marked states. So the quantum algorithm would be to apply quantum fast forwarding to generate this PTU to measure the state in the vertex basis, and then the measurement with high probability uses a marked vertex. And to prove this claim, we begin by rewriting this squared norm as bra times cat, and so then we can interpret this quantity in terms of the classical random walk. And of this cat2 means that we start at an unmarked state, then we apply t steps of the classical random walk, that's PTU. We project the state onto the marked vertices and perform t more steps of the classical random walk. And then we sort of project the state onto the unmarked vertices again. By doing this argument rigorously, we can show that indeed this square norm is precisely the probability of starting in an unmarked state, then after t steps being at a marked state, and after t more steps being at an unmarked state again. So how to prove that this probability for some choice of a good interpolation parameter, that this probability is large? To prove the statement, we analyze how the choice of the interpolation parameter affects the behavior of the random walk. And in order to do that, it is a good idea to look at the two extremes. One extreme is that we simply run the original walk, which means that when we encounter marked vertex, we probably don't stay there. And the next step, we are at unmarked state again. In order hitting time steps, we probably reach a marked vertex with high probability, but we don't stay there. So at steps t and 2t, we are at unmarked states with high probability. And a realization of random walk can be illustrated like this, with empty boxes, meaning that at the respective step we are at an unmarked state, and the red boxes signifying the steps when we are at a marked one. Now the other extreme is that we run the absorbing walk, meaning that when we reach a marked state, we stay there with probability 1. And then with high probability, both steps t and 2t, we are at a marked state. Neither of these situations are good for us because we want at step t to be at a marked state, and at step 2t be at an unmarked one. And this is where the interpolated walk comes into play, because it allows us to increase time we spend at each marked vertex. So the closer the interpolated walk is to the absorbing walk, the more time on average we spend at each marked vertex. And by tuning the interpolation parameter, we can ensure that at step t we are at a marked state, but at step 2t we are at an unmarked one. And in fact, to prove the final result, a relaxed version of the statement is sufficient for us. Namely, that the time of reaching an unmarked state after marked one, that time is allowed to differ from the time to reach a marked vertex. And we prove that this relaxation is indeed true. We show that this event happens with large probability, meaning of order at least 1 over logarithm of heating time, for a random choice of t and t prime, both of order heating time, and a random choice of interpolation parameter from a certain set. And this gives us an algorithm that finds a marked element in time which is essentially square root of the classical heating time up to logarithmic factors. These logarithmic factors appear because we lower bound this probability to be only for the 1 over logarithm of heating time. That means that at the very end we need to apply amplitude amplification. And in the follow-up work, two of our co-authors, together with Simon Apers, shows that actually the fast-forwarding subroutine is not necessary. And the same result can be achieved just by doing the interpolated work for a suitable interpolation parameter and transforming the interpolated work to a quantum work, as described by Mario Szegedi. And therefore, the interpolated work is a crucial component for the result of this kind, but the fast-forwarding subroutine is not. Thank you very much for watching this presentation, and I would like to thank my esteemed colleagues, Andrew Sambainis, Andrzej Giojan, and Stacy Jeffrey for our cooperation. Thank you.